Welcome to our Yaka Digital Network videos. Every domestic chore, from laundry to food preparation, starts with one shared requirement: water. Here in Uganda, securing it is a daily physical reality. Past the surface, a microscopic view reveals that local water sources are active chemical environments, teeming with dissolved mineral ions. The products we combine with this water, the soaps washing our uniforms, the packaged snacks we eat, the lotions applied to our skin, operate as precise chemical systems designed to interact with these specific molecules. To understand how they work, we have to deconstruct them. We need to look at the invisible forces of molecular polarity, the dissolved mineral content of our water, and the manipulation of pH levels. Mastering this chemical language provides the tools to evaluate the effectiveness and safety of every product brought into the home. Saponification converts organic fats into cleaning agents through a reaction with a strong alkali. This creates a surfactant molecule with a split architecture. The hydrophilic head carries an electrical charge, bonding with water. The hydrophobic tail repels water, binding instead to nonpolar oil and grease. During the friction of washing, the soap's hydrophobic tails bury themselves into the grease coating the fabric fibers to escape the water. Simultaneously, the hydrophilic heads bond with the outward-pulling water, lifting the grease globule completely off the fabric. This free-floating structure is called a micelle. It traps the grease inside, safely suspending it to be rinsed away. Soap doesn't destroy dirt. It acts as a molecular bridge, forcing naturally repelling substances, like oil and water, to mix through a process called emulsification. This effective mechanism faces a geographical roadblock. Many Ugandan water sources contain minerals that interfere with this chemistry. This hard water contains high concentrations of dissolved calcium and magnesium ions. When a natural soap molecule enters, these calcium ions bind to its hydrophilic head, instantly neutralizing its electrical charge. The neutralized soap clumps together, falling out of solution as an insoluble gray precipitate. This insoluble material is known as scum. It prevents lathering and deposits sticky gray stains directly back onto the clothing you are trying to clean. To solve this, chemists engineered synthetic detergents with a modified molecular structure. The calcium and magnesium in hard water cannot bind to the detergent's modified head. Remaining soluble, they form effective micelles even in heavily mineralized water, becoming the standard for industrial laundry. Environmental chemistry dictates product viability, forcing regions with hard water to shift from traditional soaps to engineered synthetics. Cleaning supplies are only one part of the matrix. We interact with engineered formulations whenever we purchase ingestible or topical products in a local market. Packaged foods rely on chemical additives called preservatives to prevent biological spoilage during transport and storage. Common preservatives like sodium benzoate lower the food's pH, creating a localized acidic environment. This targeted manipulation is hostile to microscopic threats. Spoilage-causing bacteria and fungi cannot divide under these acidic conditions, extending shelf life. Other additives, like the flavor enhancer monosodium glutamate, serve different functions. Because these compounds can trigger allergic reactions in some individuals, reading labels to identify active ingredients is a necessity. The same rule of precise chemical control governs personal care items. The human skin's natural defense, the acid mantle, requires a specific environment to remain intact, typically around 5.5 on the pH scale. Applying a highly alkaline product strips away this protective mantle, disrupting the cellular barrier and leaving the skin vulnerable. Whether we are preserving food or protecting our skin, consumer safety is entirely dependent on matching and manipulating chemical environments. This chart summarizes the trade-offs between natural soaps and synthetic detergents across their origin, efficacy in hard water, and biodegradability. Traditional soaps are highly biodegradable. When they enter the drainage system, naturally occurring bacteria can break down their organic fats, neutralizing their environmental impact. Synthetic detergents present a different reality. The chemical stability that allows them to function in hard water also makes them resistant to biological breakdown. When flushed into our water maze, they remain active as pollutants that disrupt aquatic ecosystems. We engineer synthetic solutions to solve localized challenges, like mineralized water, but we must manage the global environmental fallout of those stable chemicals. The chemical principles governing these reactions function as the underlying logic for every product in a household. Checking active ingredient lists on food and medicine allows you to balance immediate efficacy with long-term biodegradability. True chemical literacy empowers smarter, healthier choices. For more educational content and resources, visit yaka.cc.